Somewhere in the universe right now, while you are sitting here listening to this, two galaxies are colliding, not in some far-off corner of space-time you'll never have to think about again. Not as a one-time event that happened once and will never happen again. This is happening constantly, all across the observable universe in hundreds of places at once. And it has been happening since galaxies first formed, roughly 13 billion years ago. And here's the part that should unsettle you a little. One of those collisions has already been scheduled. It has a name. It has a rough date. And you, or something descended from you, might one day stand on a hillside and watch it happen with your own eyes. The Milky Way, your galaxy, the one containing the Sun, the Earth, every person who has ever lived is on a direct collision course with its largest neighbor, the Andromeda Galaxy. We know this. We've measured it. Astronomers using the Hubble Space Telescope spent years tracking Andromeda's motion across the sky with such precision that in 2012, they were able to say with real confidence that the two galaxies are moving toward each other at roughly 110 kilometers per second, and that in a few billion years they will meet. Now, if you heard the word collision and immediately pictured something violent, galaxies smashing together like cars on a freeway, stars exploding, planets being flung into the void, I want you to hold on to that image for a moment. Just hold it, because by the end of this video, that image is going to be almost completely gone, replaced by something stranger, slower, and, in a very real sense, far more beautiful. This video is going to walk you through exactly what happens when two galaxies collide, not as a metaphor, not as a simplification, but as the actual physical process, step by step, across the almost incomprehensible span of time it takes to happen. We'll talk about what the night sky will look like as it begins. We'll talk about what happens to stars, to planets, to black holes. We'll talk about what happens to the Sun and to Earth, and whether either of them survives. And by the end, I think you'll understand something that sounds like a contradiction, but isn't, that the most violent-sounding event in the cosmos might also be one of the gentlest. If this is your first time here, welcome. We make long, slow, deeply researched documentaries about the universe, the kind of thing you can put on at night, close your eyes, and just listen to. If that sounds like your kind of thing, consider subscribing. It costs you nothing, and it helps us keep making these. Okay, let's slowly ease into this. Part 1. Redefining the word collision. Let's start with the word itself, because the word is doing a lot of work, and most of that work is wrong. When two cars collide, metal meets metal. Surfaces touch. Things crumple, shatter, stop. The word collision in everyday language implies contact. Two solid things occupying the same space at the same moment, and something giving way as a result. Now, picture two galaxies. Each one is a vast disk, or in some cases a smooth ellipsoid, containing anywhere from 100 billion to over 1 trillion stars, along with gas, dust, dark matter, and at the center, almost always, a supermassive black hole. When we say these two structures are going to collide, what we actually mean is that their combined gravitational fields are going to overlap, interpenetrate, and eventually merge into a single structure. The stars themselves, the actual burning balls of plasma that make up most of what we think of as a galaxy, will, in the overwhelming majority of cases, never touch each other. Not one single star is expected to physically strike another star during the entire multi-billion-year process. Sit with that for a second. Two structures, each containing hundreds of billions of stars, are going to pass through each other, and almost nothing inside them will actually hit anything else inside the other one. How is that possible? The answer comes down to one thing. Space, even inside a galaxy, is almost entirely empty. We're going to spend the next part of this video getting a real feel for just how empty, because once you understand that, the entire rest of this video starts to make sense in a way that collision never could. Nothing touches. Everything moves. Keep that phrase in mind. We're going to come back to it. Part 2. The true scale of empty space here. is a number that sounds small until you actually think about it. The average distance between stars in a galaxy like the Milky Way is about 5 light years. 5 light years. That's roughly 47 trillion kilometers, 47,000 kilometers of essentially nothing, separating one star from its nearest neighbor. Now let's shrink that down to something your brain can actually hold. Imagine the sun shrunk down to the size of a grain of sand, about 0.5 millimeter across. On that scale, the nearest star to the sun, Alpha Centauri, would be roughly 13 kilometers away. 13 kilometers, 1 grain of sand, and then 13 kilometers of basically nothing, and then another grain of sand. Now, scale that up to an entire galaxy. The Milky Way contains somewhere between 100 and 400 billion stars spread across a disk roughly 100,000 light-years in diameter. If you were to shrink the entire Milky Way down to the size of, say, the continental United States, each star, each one of those hundreds of billions of suns, would be smaller than a single bacterium, separated from its neighbors by kilometers of empty space. This is the part that's genuinely hard to internalize, because every image you've ever seen of a galaxy, every photograph, every illustration, every artist's rendering shows a dense, glowing, almost solid-looking disk of light. That image is real in the sense that the light is real, but it's also deeply misleading because it compresses an object that is overwhelmingly empty into something that looks overwhelmingly full. A galaxy is not a solid object. A galaxy is a sparse cloud of isolated points of light, drifting through an ocean of near-perfect vacuum, held together, loosely, by gravity. So when two of these clouds begin to pass through each other, what's actually interacting isn't the stars themselves. It's the empty space between them, or more precisely, it's the gravitational fields that fill that empty space, invisibly stretching out from every star, every cloud of gas, every particle of dark matter, overlapping with the gravitational fields of the other galaxy. This is the actual collision, not matter against matter, gravity against gravity. And here's the thing about gravitational fields: they don't crash. They don't shatter. They interfere with each other the way ripples on a pond interfere, bending, distorting, reinforcing, canceling over spans of time so long that fast and slow stop meaning what you think they mean. We'll get to exactly how slow in a moment. But first, let's meet the two galaxies that are actually going to do this. Part 3. Andromeda's approach. The Andromeda galaxy, catalogued as M31, is the nearest large spiral galaxy to our own, sitting about 2.5 million light-years away. On a clear, dark night away from city lights, you can actually see it with the naked eye, a faint smudge of light in the constellation Andromeda, the most distant object most humans will ever see without a telescope. For most of human history, we didn't know what we were looking at. It was just a fuzzy patch, a nebula people called it, lumping it in with clouds of gas inside our own galaxy. It wasn't until the 1920s that an astronomer named Edwin Hubble, yes, that Hubble, the one the telescope is named after, measured its distance and realized something staggering. This wasn't a cloud inside the Milky Way at all. It was an entire other galaxy sitting outside our own, roughly the same size, roughly the same shape, separated from us by a gulf of space so large that the light reaching our eyes that night had left. Andromeda 2.5 million years earlier, before modern humans existed. That discovery alone reshaped our understanding of the universe. It told us for the first time that the Milky Way wasn't the entire universe. It was one galaxy among countless others. But there was something else hiding in that discovery, something it took decades longer to fully appreciate. When astronomers measured the light from Andromeda, specifically by analyzing its spectrum, the way certain wavelengths of light shift depending on motion, they found something unexpected. Most distant galaxies show what's called a redshift. Their light is stretched toward longer, redder wavelengths because they're moving away from us. Carried along by the expansion of the universe itself, Andromeda shows the opposite, a blue shift. Its light is compressed toward shorter wavelengths, which means, unambiguously, that Andromeda is moving toward us. For a long time, that's about as much as we could say. We knew Andromeda was approaching. We knew roughly how fast at about 110 kilometers per second, which sounds incredibly fast until you remember the distances involved and then sounds incredibly slow. But knowing it was approaching in a straight line toward us wasn't enough to know whether it would actually hit us. A galaxy could approach for billions of years and then sweep past at an angle, missing entirely. The cosmic equivalent of two ships passing in fog. The answer to that question, does it hit or does it miss, required something extraordinarily difficult to measure: Andromeda's sideways motion. Its motion across the sky perpendicular to its approach, and measuring that meant detecting a shift so subtle across an object so distant that it had never been reliably done before. In 2012, using the Hubble Space Telescope, a team led by astronomer Roland van der Marel finally did it. By comparing images of Andromeda taken years apart, they measured its proper motion, its actual sideways drift across the sky, and found that it was, within the margins of measurement, essentially zero. Andromeda isn't just approaching us, it's coming almost straight at us. This is going to hit, not might, will. Barring something we don't currently understand about either galaxy's structure, the Milky Way and Andromeda are on a collision course, and that collision is not a possibility we're speculating about. It's a measured trajectory with real numbers attached to it. So let's talk about those numbers. Let's talk about the timeline. Part 4, the timeline. Here's the headline number. The Milky Way and Andromeda are expected to begin merging in roughly 4 to 4.5 billion years. Let that number sit there for a second because it's the foundation everything else in this video is built on, and it's a number so large that your brain almost certainly cannot represent it as anything other than a really long time. So let's break it down into something more graspable. The universe itself is about 13.8 billion years old, so 4.5 billion years from now represents roughly a third of the universe's entire current age, added on top of everything that's already happened, every star that's ever formed, every galaxy that's ever taken shape, the entire history of life on Earth, all of it. To put it in human terms, complex multicellular life has existed on Earth for roughly 600 million years. The collision is scheduled for about 7.5 times further into the future than that entire span of life's history stretches into the past. And here's the part that often gets lost. 4.5 billion years from now isn't the moment of impact, it's the beginning. The actual merger, the full process, from first contact to final settled result, is expected to take an additional 2 to 4 billion years after that. Some models stretch the entire process, start to finish, to something closer to 6 or 7 billion years total. This is not an event, it's an era. If you tried to compress the entire collision into a single year, say, January 1st is first contact and December 31st is fully merged and settled, then a single human lifetime, all 80-odd years of it would occupy roughly nothing, a fraction of a second. You would not be able to perceive that anything was happening at all, even if you were watching the whole thing unfold in front of you, your entire life, start to finish. And yet, and this is the part I find genuinely strange, if you could somehow live through the early stages of this, if you could stand on a hillside on some future Earth and look up at the night sky once every few million years, you would absolutely be able to see it happening. Not all at once, but across enough time, the sky itself would visibly, dramatically change. So, let's go there. Let's talk about what the sky is actually going to look like. Part 5. First contact a changing sky right now. If you go outside on a dark night and find Andromeda, it looks like a faint smudge, roughly the size of the full moon in apparent diameter, though far too dim for most people to perceive its full extent without a long exposure photograph. Now fast forward. 2 billion years from now, Andromeda is closer, significantly closer, and the change in the sky is no longer subtle. It's now a visibly larger, brighter patch of light, an unmistakable second presence in the night sky alongside the familiar band of the Milky Way's own disk. Keep going. 3.5 billion years from now, Andromeda now fills a significant portion of the sky, not as a point of light, but as a vast, glowing structure, its spiral arms potentially visible to the naked eye, stretching across a huge swath of the heavens. At this point, anyone, or anything looking up would know unambiguously that something enormous is approaching. And here's where it gets genuinely strange. As Andromeda grows larger in the sky, something else starts happening. Tidal forces, the same kind of gravitational stretching that causes ocean tides on Earth, but on a galactic scale, begin to distort both galaxies. Streams of stars and gas start to get pulled out of each galaxy's disk, forming long, faint, glowing arcs and tails that stretch across enormous distances. These tidal tails have actually been observed in other colliding galaxy pairs throughout the universe. They're not speculation. They're documented phenomena, visible in telescope images of galactic collisions happening elsewhere right now. So the sky during this phase wouldn't just show two galaxies approaching each other. It would show two galaxies beginning to visibly deform, long luminous streamers of stars being drawn out into space, arcing between the two structures, like the beginnings of some vast cosmic bridge. If you're picturing something dramatic, you're not wrong. This would be, by any definition, one of the most spectacular things a planet's sky could ever display. But here's the key thing, and this is something we're going to come back to. All of this would unfold so slowly that no single observer, no single generation, no single civilization even, would necessarily perceive it as an event. It would just be the sky slowly, over millions of years, becoming something else. What would it feel like to stand under a sky like that? We'll come back to that question. For now, let's go inside the collision itself, because something remarkable starts happening to the galaxy's gas, long before the stars themselves do anything dramatic at all. Part 6. Gravitational Choreography. So far, we've been talking mostly about what an outside observer would see. Now, let's talk about what's actually physically happening to the two galaxies as structures. As Andromeda and the Milky Way approach each other, their gravitational fields begin to overlap and interact, and the first, most dramatic effect of this isn't on the stars, it's on the gas. Both galaxies contain enormous reservoirs of interstellar gas, mostly hydrogen, drifting through the disk in clouds of varying density. Unlike stars, which are effectively point-like objects separated by vast distances, gas is more like a fluid. It fills space. And fluids, when they're subjected to colliding gravitational fields, do something stars don't. They can actually collide. Gas clouds from one galaxy can physically slam into gas clouds from the other. When that happens, the gas compresses. Shock waves ripple through it. And compressed gas, under the right conditions, does something specific. It collapses under its own gravity and forms new stars. This is one of the most counterintuitive facts about galactic collisions, and it's worth sitting with. The early to middle stages of a galaxy merger don't destroy stars. They create them, in huge numbers, in a burst of star formation so intense that astronomers have a specific term for it: a starburst. We've actually observed this happening in real time, in other colliding galaxy pairs across the universe. The Antennae galaxies, a famous pair of colliding spirals about 60 million light-years away, are in the middle of exactly this process right now. And observations show regions of incredibly intense star formation, producing new stars at rates dozens of times higher than a normal, undisturbed galaxy. So before anything ends, in a sense, something begins. The merger of two galaxies is, for a significant stretch of its timeline, also one of the most fertile periods of star formation either galaxy will ever experience. Meanwhile, the gravitational choreography continues on a larger scale. As the two galaxies make their first close pass, and close here still means tens of thousands of light-years, an almost incomprehensible distance, but close in galactic terms, their mutual gravity begins to distort both disks dramatically. Spiral arms get stretched, twisted, sometimes torn apart entirely. The orderly pinwheel structure that both galaxies have maintained for billions of years starts to break down. And this doesn't happen in one pass. This is the part that surprises a lot of people. Galaxies don't typically merge in a single collision. They swing past each other, gravity slows them down, and they fall back toward each other again, sometimes 2, 3, or more times over the course of 1 billion years or more, like two dancers spiraling slowly toward each other, getting closer with each pass, before finally settling into a single combined embrace. Each of these passes would, if you could watch from a safe distance, look spectacular. Tidal tails flung out further, gas compressed into glowing starburst regions, the two galactic disks visibly warping. And each time, the two galaxies would separate again afterward, before gravity pulled them back for another pass. It's less like a car crash and more like two slow-motion waves washing over each other, retreating, and washing over each other again, each time leaving the shoreline a little more changed than before. Nothing touches. Everything moves. Part 7. The Starburst. Let's slow down on the starburst phase because I think it's one of the most important and most overlooked parts of this entire story. When people imagine a galaxy collision, they tend to imagine destruction, endings. And in the very long run, in some sense, that's true. Both galaxies, as distinct structures, will eventually cease to exist. But on the way to that ending, something happens that looks almost like the opposite, an explosion of creation. As gas clouds from the Milky Way and Andromeda interpenetrate and compress, regions of intense star formation light up across both galaxies, and especially in the regions where the two galaxies' gas reservoirs overlap most directly. New stars form by the millions. Many of these will be massive, short-lived stars, the kind that burn hot, bright, and blue and live for only a few million years before dying in supernova explosions. So during this phase, the merging galaxies wouldn't just look brighter because of the approaching second galaxy. They'd look brighter because entire new regions of intense, blue-white star formation would be igniting, and, on the timescale of millions of years, also dying in waves of supernovae that would themselves briefly outshine entire star clusters. Here's a number worth sitting with. In a typical starburst galaxy, star formation rates can reach 10, 50, sometimes over 100 times the rate of a normal galaxy like the present-day Milky Way, which forms roughly 1 to 2 new stars per year on average. A starburst triggered by a galaxy merger could, for a period of tens of millions of years, be forming new stars at a rate of dozens per year. A firestorm of stellar birth, lit by the gravitational disturbance of two galaxies falling into each other. And all of this, every bit of it, would be happening while the stars that already existed in both galaxies continued on, almost entirely undisturbed, drifting through their newly warped galactic disks, their orbits gradually being reshaped by the changing gravitational landscape around them, but not colliding, not burning up, not destroyed. Two galaxies falling into each other across billions of years, igniting a fireworks display of new star formation that would itself last for tens of millions of years, all while the existing stars in both galaxies simply kept doing what they were doing, orbiting, shining, existing. This is the part of the story that collision completely fails to capture. There's an entire act of creation embedded inside what sounds, from the outside, like an act of destruction. But there is one part of this story where something genuinely dramatic, genuinely violent, in the truest sense of the word, does eventually happen. And it's not about stars at all. It's about what's waiting at the center of each galaxy. Part 8. The Black Hole Dance. At the center of the Milky Way sits a supermassive black hole called Sagittarius A, with a mass of about 4 million times that of our Sun. At the center of Andromeda sits its own supermassive black hole, considerably larger, estimated at somewhere between 100 million and 200 million solar masses, depending on the measurement method used. During the early stages of the merger, the passes, the tidal tails, the starburst, these two black holes remain exactly where they've always been. at the gravitational centers of their respective galaxies, tens of thousands of light years apart, completely unaffected by anything happening in the outer disks. But as the merger progresses, as the two galaxies make repeated passes and gradually lose orbital energy to gravitational interactions with each other's stars and gas, the centers of the two galaxies themselves begin to drift toward each other, and at the heart of each center sits one of these black holes. Eventually, and eventually here means probably over the span of 1 billion years or more after the initial collision begins, the two supermassive black holes find themselves orbiting each other, locked in their own gravitational dance. Much smaller in scale than the galaxy-wide interactions, but vastly more intense. This is where things get genuinely violent by any definition of the word. As the two black holes spiral closer together, losing energy with each orbit, primarily by flinging nearby stars away in gravitational slingshot interactions, they eventually reach a point where they're close enough that a different process takes over: the emission of gravitational waves. Ripples in space-time itself, predicted by Einstein over a century ago and directly detected for the first time only in 2015 by an instrument called LIGO. As the two black holes spiral ever closer, emitting gravitational waves, they lose orbital energy at an accelerating rate, until, in the final moments, they merge. Two supermassive black holes, one with a mass in the millions of suns and one with a mass in the hundreds of millions, collide and combine into a single, even more massive black hole, releasing in that final instant an amount of energy that, for a brief moment, could outshine every star in both galaxies combined, radiated not as light, but as pure gravitational waves rippling outward through the fabric of space-time itself. This event, a supermassive black hole merger, has never been directly observed. We've detected gravitational waves from much smaller black hole mergers, the kind involving black holes a few dozen times the mass of the Sun, a merger on the scale of two supermassive black holes, each containing the mass of millions or hundreds of millions of stars, would be almost unimaginably more powerful, and is, as far as we know, an extraordinarily rare event in any individual galaxy's lifetime. And it's coming, eventually. Buried somewhere inside the multi-billion-year process of the Milky Way and Andromeda merging is a moment, a final, climactic moment, where the two supermassive black holes at their hearts finally come together, and the universe for an instant rings like a bell. But here's the thing about that moment. By the time it happens, both galaxies, as distinct entities, will have ceased to exist for a very long time already. The black hole merger isn't the climax of the story in any narrative sense. It's just the last piece, the final settling of the largest masses involved, happening long after almost everything else has already found its new place. So where does that leave everything else? Where does it leave the Sun? Where does it leave Earth? Part 9. The Sun's Fate and Earth's. This is, for a lot of people, the question that actually matters. Forget the black holes, forget the tidal tales. What happens to us? What happens to the Sun, to the Earth, to the solar system during all of this? And here's where I have to give you some important context first. By the time any of this is happening, the Sun itself will already be in serious trouble, entirely independent of Andromeda. The Sun is roughly 4.6 billion years old, and it's expected to remain in its current stable, hydrogen-burning phase for roughly another 5 billion years. After that, it will begin to swell into a red giant, eventually expanding to a size that may engulf Mercury, Venus, and quite possibly Earth itself, though the exact fate of Earth in that scenario is still debated, partly because the Sun will also be losing mass during this process, which would loosen its gravitational grip on the inner planets. The point is, the timeline of the Sun's own death and the timeline of the Andromeda collision substantially overlap. The collision begins around 4 to 4.5 billion years from now. The Sun's red giant phase begins around 5 billion years from now. These aren't sequential events, they're roughly concurrent, unfolding across the same vast stretch of cosmic time. So when we ask what happens to Earth during the galaxy collision, we have to be honest about something. depending on exactly how things play out, Earth and the Sun itself may already be in the process of a completely separate transformation, driven entirely by the Sun's own internal evolution, regardless of anything happening with Andromeda. But let's set that aside for a moment and ask the question in isolation. Assuming the Sun and Earth are still roughly as they are now, what does the galaxy collision itself do to them? And the honest, research-backed answer is, almost certainly, not much. Remember Part 2, the true scale of empty space. The Sun is one star in a galaxy of hundreds of billions, separated from its neighbors by trillions of kilometers of empty space. As the Milky Way and Andromeda pass through each other, the overwhelming likelihood, based on simulations of galaxy mergers, is that the Sun and its solar system simply continue existing largely undisturbed, possibly nudged onto a somewhat different orbit within the newly forming combined galaxy, but not destroyed, not ejected into intergalactic space. Though that's not impossible, some stars probably will be flung outward during the merger, and almost certainly not involved in any kind of direct collision. Some simulations suggest there's a small but real chance, often cited as somewhere in the range of a few percent, that the solar system could be pulled toward and end up orbiting closer to the new combined galaxy's center, or alternatively flung outward toward its outskirts. But the dominant outcome across most simulations is simply things continue. The Sun keeps shining, the solar system keeps orbiting. Just now, around the center of a different, larger combined galaxy than the one it started in. If there were still something alive on Earth, or somewhere else in the solar system, to look up at the sky during all of this, what would they actually see at the moment of merger? Probably a sky full of stars, a lot of stars. The combined galaxy would be denser in places than either original galaxy was, more stars visible, a brighter band of light across the sky, possibly a more prominent galactic core, but not a sky full of streaking, colliding stars. Not chaos, just more, a fuller sky. That's perhaps the simplest, truest way to describe what an observer would actually experience, if they could experience any of this at all. Part 10. The merger itself. So let's pull all of this together and walk through the merger as a single, sequential process, acknowledging as we go that sequential is doing a lot of work here, given that we're talking about a sequence that unfolds over several billion years. First, the long approach. For roughly 4 to 4.5 billion years, Andromeda and the Milky Way close the distance between them, currently about 2.5 million light-years, at a relative speed of around 110 kilometers per second. During this phase, the night sky of any observer in either galaxy would slowly, almost imperceptibly, begin to change, as Andromeda grows from a faint smudge into a visibly large structure in the sky. Second, first contact and the initial pass. The outer reaches of both galaxies' gravitational fields begin to interact. Tidal forces stretch both disks, pulling out long streams of stars and gas, the tidal tails. Gas clouds from each galaxy begin to collide and compress, triggering the first wave of intense star formation. Third, separation and return. The two galaxies don't simply merge on contact. They swing past each other, slowed by their mutual gravity and by the drag of interacting with each other's stars and gas, a process astronomers call dynamical friction, and then fall back toward each other for another pass. This can repeat multiple times over the course of roughly a billion years, each pass further disrupting both galaxies' original spiral structure. Fourth, structural collapse. With each pass, the orderly spiral structure of both galaxies degrades further. Spiral arms unwind, get stretched into tidal tails, and lose their coherence. By this stage, neither galaxy would really look like a spiral anymore. Both would be transitioning into something more chaotic, more diffuse, a swarm of stars no longer organized into the elegant pinwheel shapes we associate with spiral galaxies. Fifth, the central merger. The two galactic centers and the supermassive black holes at their hearts gradually spiral toward each other, a process that itself can take a billion years or more, eventually culminating in the black hole merger we discussed in Part 8. Sixth, settling. Over the final stretch of this process, potentially another billion years or more, the combined mass of both galaxies gradually settles into a new, stable configuration. The chaotic, disturbed shape left over from the merger relaxes under gravity into something smoother, rounder. And what does that final shape look like? Part 11, Milky. The combined galaxy that results from this entire process has, somewhat informally, been given a name by astronomers Milky, a portmanteau of Milky Way and Andromeda. Based on simulations, Milky is expected to be an elliptical galaxy, a smooth, roughly egg-shaped or spherical distribution of stars lacking the spiral arms, the disk, the elegant pinwheel structure that both progenitor galaxies currently have. This is, in its own way, one of the most poignant outcomes of the entire process. Two of the most structurally beautiful objects in the observable universe, grand spiral galaxies, with their sweeping arms, their organized disks, their clearly defined structure, would, over billions of years, gradually lose that structure entirely, settling into something far more amorphous, not destroyed, not gone, just different, reorganized. The same stars, largely the same mass, the same black holes, now merged into one, but arranged in a fundamentally different shape. Elliptical galaxies, interestingly, are common in the universe, and many of them are believed to have formed through exactly this process. The merger of two or more spiral galaxies over billions of years, gradually losing their organized structure and settling into a smoother, rounder shape. In a sense, by studying ellipticals elsewhere in the universe, we're looking at galaxies that have already been through what the Milky Way and Andromeda are scheduled to go through. We're looking at the future, already arrived somewhere else. Milky would likely be significantly larger and brighter than either progenitor galaxy individually, containing the combined stellar mass of both, plus whatever new stars formed during the starburst phases. It would also likely contain a single, much more massive central black hole, the merged product of Sagittarius I, and Andromeda's central black hole. And somewhere within it, if everything we discussed in Part 9 holds, would be the Sun, or whatever the Sun has become by that point, orbiting within a structure that no longer resembles either of the two galaxies it was born between. Part 12, the final ring. Let's go back to the black holes for a moment, because I want to give this its proper weight. We talked about the eventual merger of Sagittarius A and Andromeda's central black hole, a combined mass that could be somewhere in the range of 100 to 250 million times the mass of the Sun, depending on how much each black hole grows during the merger process itself. Mergers often trigger increased feeding of central black holes, as gas gets funneled toward galactic centers during the chaos. When two black holes of this scale finally merge in the last fraction of a second of a process that's taken over 1 billion years to unfold, the energy released, in the form of gravitational waves, would be staggering. We're talking about an event that, for a brief moment, could release more energy than the combined light output of every star in both galaxies, not as light, but as ripples in the structure of space-time itself, propagating outward at the speed of light, passing through everything in their path, stretching and compressing space itself by infinitesimally tiny amounts as they go. We've detected gravitational waves before. LEGO's first detection in 2015 came from the merger of two black holes roughly 30 times the mass of the Sun, located about 1.3 billion light-years away. That event was already one of the most powerful things humans had ever indirectly observed. A supermassive black hole merger, the kind that would eventually happen at the heart of Milky, would involve masses millions of times larger. The gravitational waves produced would be correspondingly more powerful, though also at a much lower frequency, requiring different kinds of detectors than the ones we currently use. This is, in fact, one of the major goals of future space-based gravitational wave observatories currently being planned. This event, this final ringing of space-time, represents, in a sense, the true end of the Milky Way and Andromeda as separate entities. Not the first contact, billions of years earlier, not the starburst or the tidal tails or even the broad structural merger into an elliptical shape. The actual final unambiguous moment where the very last distinct remnant of two galaxies becomes unambiguously one is this. Two black holes, each one the gravitational anchor of an entire galaxy, finally becoming a single black hole, and announcing that fact to the rest of the universe in the form of a ripple in space-time itself. And by the time that happens, by the time that ring goes out, everything else will have settled long before. The starburst will be ancient history. The tidal tails will have long since dispersed or fallen back in. The elliptical shape of Milky Way will already be well established. This final event is less a climax and more like the closing of a book that finished its story chapters ago and is only now being formally shelved. Part 13. This is happening everywhere. Here's something I think is easy to lose sight of after spending this much time focused on one specific collision. The Milky Way and Andromeda are not special in the sense of being unusual. What's about to happen to them has already happened, and is happening right now, to countless other galaxy pairs across the observable universe. Galaxy collisions and mergers are on cosmic timescales common. They're part of how galaxies grow. Many of the largest galaxies we observe today, including giant elliptical galaxies at the centers of galaxy clusters, are believed to be the products of multiple past mergers. Galaxies that have absorbed smaller companions or merged with similarly sized partners repeatedly over billions of years. We can observe this process directly because the universe is so large and light takes so long to travel that looking at distant galaxies means looking back in time, and at various points in cosmic history, we can see galaxy pairs in every stage of the merger process we've described. Galaxies just beginning to interact. Galaxies in the middle of dramatic tidal interactions with long, glowing tails of stars and gas, galaxies that have already merged into disturbed, irregular shapes still settling into their final form. The antennae galaxies, which we mentioned earlier, are a real example of the mid-stage starburst phase. Two spiral galaxies, currently passing through each other with spectacular tidal tails and regions of intense star formation, located about 60 million light-years away. We're not speculating about what that looks like. We have images of it. It's happening right now as you listen to this. Or rather, it was happening 60 million years ago, and the light from that event is only reaching us now. So in a sense, what we've spent this entire video describing isn't really a prediction about some unique, far-future event. It's a description of a normal, recurring process in the life of galaxies, one that the Milky Way and Andromeda happen to be scheduled to go through next. On a timeline we can actually calculate, because they happen to be close enough and moving in the right direction for us to measure it. Every large galaxy you can see in the night sky, every smudge of light, every faint spiral, has in its past very likely already absorbed other, smaller galaxies. And many of them, like the Milky Way and Andromeda, have larger mergers still ahead of them. The universe is not a static collection of separate islands. It's a slow billion-year dance of objects falling toward each other, passing through each other, and becoming something new, over and over and over again, on timescales so vast that from any single vantage point, in any single moment, it simply looks like a sky full of stars, unchanging, eternal, until you wait long enough. Part 14, what this means. So here's where we end up. Two galaxies, each containing hundreds of billions of stars, each with its own supermassive black hole, each with its own 4 billion-year history of formation, evolution, and quiet orbital motion, are going to spend the next several billion years slowly, gently, almost imperceptibly, becoming one. Along the way, almost nothing will actually collide. Stars will pass each other at distances of trillions of kilometers, oblivious. New stars will be born in numbers far exceeding anything happening in either galaxy today. An explosion of creation triggered by the gravitational disturbance of the approach. Existing stars, including quite possibly the Sun, or whatever remains of it, will simply continue, nudged onto new orbits within a new, larger, differently shaped galaxy, but fundamentally intact. And at the very end, so far in the future that it's almost a separate event in its own right. Two black holes, each one the gravitational heart of an entire galaxy, will finally merge, and the universe will ring briefly, with the echo of that union. If you set out at the beginning of this video expecting a story about destruction, about violence, about endings, I hope what you found instead was something stranger, a story about transformation. About two things, each beautiful and complete in their own right, slowly becoming a third thing, different from either, but not lesser. Not a wreck, a new shape. There's something in that, I think, that extends beyond galaxies. We tend to think of collision as a word that only means damage, something breaking. But the example the universe gives us, the actual physical measured example, happening on a schedule we can calculate, is one where two enormous, complex, beautiful structures pass through each other. And what comes out the other side isn't wreckage. It's something new, something that didn't exist before, made entirely from the pieces of what did. 4 billion years from now, give or take, the sky over wherever the Earth happens to be, if the Earth is still anywhere, still itself, still turning, will look different than it does tonight. Fuller, stranger, lit by a galaxy that doesn't exist yet, made from two that right now, tonight, are still moving toward each other across a gap of 2.5 million light years. In near total silence and near total emptiness, at a speed that feels on any human scale impossibly slow, and yet is, on the only scale that actually matters, exactly fast enough. Nothing touches, everything moves, and somehow out of that, and eventually, something new. That's it for this one. If you found this interesting, there's a lot more where this came from. Long, slow, deep dives into the universe. The kind of thing you can put on, close your eyes, and just listen to. Consider subscribing if you'd like more of this. Until next time, sleep well.